In this video, we're going to take a brief look at a few more concepts that are associated with sets. In a previous video, we looked at the concept of the empty set, which is the set that contains no elements, and it has some special notation. So just as a reminder, we used either that symbol or that symbol to indicate the empty set. Well, it turns out there is another concept which is kind of the polar opposite of the empty set, and it's called the universal set. So the universal set is simply a set that contains everything that's being considered, right? So the universal set contains all elements being considered, right? So again, what do we mean by being considered? Well, sometimes, for instance, let's say in Calculus 1, when you learned about the derivative, well, then you essentially went on and you learned about all the properties of functions that are differentiable, right? So in that context, we were considering differentiable functions, and then pretty much any function that fits that definition would be fair game in a course like that. So it's not necessarily saying everything in the entire universe, in like the physical universe, but more precisely everything that we are studying. So what is the notation for that? Well, we use a fancy U, right? So this is the notation for the universal set. Now, with the empty set and the universal set, it now allows us to start defining some set operations and then some other things, right? So what we're going to do now is essentially list some of the standard set operations, and then again talk a little bit more about their properties, so you get more accustomed to those operations. So this is like a little sub bullet. So set operations. All right. So what we're going to say is, let me make this general statement. So given two non-empty sets, call them A and B, right? We define the following operations. And some of these are very, very basic. Some of them you may already know, depending on how much work you'd have done with sets, right? So, and probably the best way to think about this is think of like operations that you can do with numbers, right? So like if I give you two numbers and I say add them, you know what to do. Or if I say multiply them, you know what to do, and so forth. It's a similar type of thing with our set operation. So the first one is called the union, right? And its notation is just, it looks like a right side up U, right? It just doesn't have the little curly tail there, depending on how you write it in script, right? So let me write it down. So A union B, what does this produce? This is the set of all elements. Oh, I forgot my L there, or LE. So it's the set of all elements that are in A or B or both, right? So basically, this is what we refer to in as the inclusive OR. Those of you who've done a little bit more like Boolean algebra and you're familiar with things like, inclusive and exclusive ORs. In set theory, the union is equivalent to the inclusive OR, and it produces a set that has all the elements that are in A, all the elements that are in B, and then all the elements in both of them. So even if they have elements in common, those elements show up in the union. Next operation. So I'm just gonna list like 3 operations and then just do a couple examples to wrap up this video. So this is going to be a relatively short one. The next operation is the intersection, right? And that one, it's take the U and just flip it upside down, right? So that's the symbol for intersection. So A intersect B, that produces another set, and it is the set of all elements that are in A and B, right? So they have to be in both. So essentially the intersection, it produces another set that has all the elements that are common to both A and B, right? So again, very simple operation. And then the third one that we will cover it's called a complement, and it's spelled with the E there, not an I. So it's not like you're paying someone a compliment saying, hey, you're pretty cool, or hey, you're really good at soccer. It's not that kind of compliment. This is a mathematical complement, and it has 2 notations. Either it's denoted with a line above the set, the name of the set, or with a superscript of a C. So yeah, it looks like, I'll write it below with an actual set. But if we have A, so it's either denoted like this or like that. Now, I'm mentioning both because if you look at other resources, you'll see these 2. In fact, if I'm giving you alternative notations, here's another one. Sometimes you might see, in this context, you might see it as an asterisk, right? Now, to be consistent, we're not going to be, in this course, we're not going to be utilizing lots of different notations. I'm just going to use the more popular one, or maybe the most popular one, is the A with the horizontal line on top, right? So you can think of it, you can read this as like A bar. So you can read this one as A bar, which might be a little bit confusing because there are other things in this course which will be denoted by a bar, but the context will be clear. All right. So what is the complement? So it's another set. So it's a set of all elements in the universal set. So it's in your universe. So in U, but not in A, right? So it's in the universal set, but not in A. And that's our complement. All right. So let's look at an example to illustrate these different operations. So let's do an example. Now, when you're given a question involving sets and you're asked to do operations, the question to be well defined, in other words, for the question to be well posed, a universe has to be defined. So here's our universal set. I'm just going to use sets of letters. So A, B, C, D, E, F, G, and H. So this is our universal set. And then I'm going to define 3 other subsets of this universal set. So I'm going to say set A consists of A, E, D, and G. Let's say set B contains the elements A, B, C, I forgot my comma here, and H. And then let's say set C is D, E, F, and G. All right, and let's just do walk through a few examples where we use these operations. So let's start with example 1. Let's say I wanted us to find A union B. All right, so the union consists of the set of elements that are in A or B or both. So they both have an A in there. Even if they only one of them had the element A, this would be in our union. And I'll just try to do it alphabetically. Then I have a B and a C here. So B, C, and then I have a E and a D. So I'll put those alphabetically. So remember, the order doesn't matter in a set. Doesn't matter, right? So we have A, B, C, D, E. There's no F, and then there's G, and then H. So G, and then H. So this set here represents the union of both of the sets A and B. Now, what if we were to look at the intersection? So A intersect B. Well, so the intersection consists of all the elements that A and B have in common. So they have an A in common for sure. E is not a common element between the two, neither is B, nor C, nor D, nor G, nor H, and that's it. So there's nothing else. I'll close this one, and here we have the intersection of A and B, right? Now, what if we wanted to find, let's say, the complement of A union with C? All right, so let's try to do a combination here, where this is saying find the complement of A and then take that set and form the union with set C. So so this is an example where you have multiple operations. And just like how when you're doing arithmetic or you're doing algebra, you can have one expression that has multiple operations. Same thing when you're dealing with sets. So what I'm going to do is this. I'm going to write it out. So A is the set A, E, D, G. And we have to take the complement of that. And then I have to do the union with set C, which is D, E, F, G. Okay, so let's go ahead and write down first what the complement is. So let's figure out all the elements that are in the universal set, but not in A. So B, right, is in the universal set, but is not here. So we have B, we have C is in the universal set, but not in A. D and E are in A, so it can't be in its complement. And then F and H round out the complement of A, right? And then I still have to do the union with this set, D, E, F, G, right? Now the union just says take all these elements and all these elements and form a new set. And when we're listing that set, as previously discussed, we don't need to list elements multiple times. It's not incorrect. It's not considered, standard practice. So again, I'll try to do these alphabetically. So we have B, C from these two, and then we have D, E from these two. So D, E, and then we have F common in both, but that's fine. The union has everything. And then E, F, G, H. So then G and H. And that's the complement of U, union C. Let's do one more example. And so let's say we had B intersect C, but then take the complement of all of that, right? So here again, I wanted to do another example with two operations, but in a slightly different way. In example 3, we did the complement of A first and then did the union with C. Now we're going to have to do the intersection first between B and C and then take the complement of the result. So again, I'm going to write everything out in sets. So first I'm going to write B. So that's A, B, C, H. And then I have to intersect that with D, E, F, G. And then take the complement of that, right? Well, let's see what happens. Doing the intersection first, well, these two sets, they have nothing in common, like no elements in common. So what does that mean? It results in the empty set, right? But then I have to take the complement of the empty set. And as I said earlier, the empty set and the universal set are like opposites of each other. So if you take the complement of the set that has no elements in there, you're going to end up with the set that has all the elements under consideration. So here you'll end up with U, right? So that wraps up the 4 examples. Before we end the video, I just want to introduce another term. In general, when you have two sets that have no elements in common, we say that those sets are disjoint. So I'll say this. So note, if A and B have no elements in common, so have no elements in common, and what that means, from a set operation standpoint, I'll just say that is A intersect B is the empty set, right? So if they have no elements in common, we say A and B are disjoint, right? Like that. Or another phrase that's used, are mutually exclusive, right? So they have nothing in common. And those are the two terms, right? So I just wanted to, again, introduce a few basic operations, do a couple examples, and then just a few more concepts and terms that are associated with sets as we kind of go through this kind of abbreviated introduction to sets. Not very deep, but just enough to get us comfortable with the lingo and with operations that are associated with them. So hopefully you found this video interesting and informative, and I will see you in the next video.